comparison. So, ladies and gentlemen, in your take-home exercise, I had asked you to go and create a hybrid model of sorts, a model that that involves the same basic phenomena characterized with the agent-based model, but did so in a way that that also had a system dynamics characterization, a high-level aggregate characterization. So just to remind us, the agent-based model here was a model of what? Can anyone say? Okay, it was a model of infection, and it involved a situation where an individual cycled from susceptible, exposed, infected, and recovered, right? And then they would go back to susceptible. Now, what was the behavior of that model left, if we considered it in isolation? If we considered that in isolation, and maybe I'll go load it in isolation so we don't tip our hand too much with respect to the comparison. What was the behavior of this model that we saw in the closing minutes of class? Can anyone characterize the type of behavior that comes out of this model? So just as a reminder, we have people going between those states, right? And so they spent a certain amount of time in this latent state where they weren't obviously infected. They couldn't transmit the infection. We would seed the infection here by clicking on particular items here. Now, this is exhibiting truculence. Of course, it's finished. Okay, we'll be able to explain that later. Here we go. Okay, boom. And what will happen if I seed the infection like this? Anyone say? Does it always take off?
Not always.
Does it sometimes take off? Yes. So what's going on there? Why does it sometimes die out? Why does it sometimes take off?
Because of the random seed.
Yeah, there's randomness. I mean, sometimes it catches, sometimes it doesn't, even when clicking on for the same person, because it's going to be generating different random numbers. Does this infection stay present for very long periods of time?
It can.
It can. Okay. What just happened? Let's try that again. So we're going to start this up. Here we go. I will start that. What just happened?
Got to a point where everyone was susceptible and no one was infected.
Okay, was that in equilibrium?
Yes.
Is this in equilibrium right now? From the standpoint of the count of people infected?
No.
Well, yeah. No, not right now. And what leads it to change suddenly to a situation where you have something like this? Yeah, so it's partly a matter of happenstance, right? The luck of the draw, nobody has gotten infected recently to keep the infection going, and it goes back to this disease-free equilibrium. Is this a stable equilibrium? Is this an equilibrium that persists despite disturbance? It's not very stable. I mean, it's hard to give a complete answer with that without mentioning the stochastics involved, right? I mean, after all, stability is not absolute here. In other words, this might be stable, or it might resist perturbation, but often it does not, right? Because of the stochastics involved. So here we do have a situation where the infection can take off, or it can not take off depending on the luck of the draw, the random numbers associated with it. If it does take off, it can go extinct by the luck of the draw at certain points, and it will get back to a state where it's not stable in in an absolute sense, a lot of the times it will take off. So there's a lot of stochastics here. Now, how do you think this would change if I were to double the size of the population? And let's say make the space correspondingly large. How do you think that would change things? In terms of whether the infection dies out or not.
Might reduce the odds that the infection dies out.
Yeah, it reduces the odds of that strange coincidence where individuals just happen to have their infections coordinated so it doesn't catch. How if it were 100 times as large? Do you think we'd see this die out occur as often?
Probably more often due to the connections, number of connections. Get out bigger space.
Okay, how if the space size were equally larger? 100 times larger area, 100 times larger number of agents? Turns out that, once again, Rowan's reasoning holds. It's less likely to die out. I mean, after all, it might die out in 1/4 of the space, but not another. Now, you'll notice that I'm talking about things, though. I'm implicitly alluding to things here which are germane. I mean, one thing is the density of the space. Let's suppose that we double the size of the population without growing the space here. Okay, we're going to copy this baseline. We're going to paste it in. Boom. And we're going to change the population size from 250 to 500. Okay. And this will be population 500. Do you think that will change the dynamics in terms of the fraction of people infected? What do you think? We have something like this, same space. Do you think the prevalence of infection would be the same or different? Anyone?
It'll increase.
And why will it increase?
You have more connections and
Yeah.
folks are less likely to pass it on and pursue it.
Good. Okay. So I like that idea. Let's probe that issue a little bit further. So I'd remind you that where in this model is contact occurring? How is transmission occurring? It's via contact. Where is contact occurring on this model? Yeah, it's inside of the infective. And it's occurring at what? At an amount per day that's given by this contact rate, right? Ladies and gentlemen, we're keeping contact rate the same between this and this. But is the prevalence of infected, the contact rate is the same. I mean, after all, it's saying contact. Why do you think the results will be different? Well, to sharpen this a little bit, let's close this model. I'm going to open the model that I did for the this take-home exercise. Okay, there we go. Here we go, and here we have basically the same situation, except we're benefited by some graphs, and we're benefited by some stocks and flows. Okay, and we're going to look at this. At first, our attention predominantly will be on the ABM. Okay, okay. So let's run this thing. Let's run it here with the population size 250, and let's check what the sort of level of prevalence goes to. It died out. I should have been quicker. Okay, let's run it a bit slower here. Here we go. And what's going on at first? Well, it rises quickly. You notice it's exponential, right? Each infective is surrounded by lots of people around them that are susceptible. One infection goes to 2, goes to 4, goes to 8, as each of those people experience the infection. And, you know, the level of infection varies over time, the number of people infected, but it tends to oscillate somewhere around, well, this one here is not a bad approximation, somewhere around 30 some odd, right? It's kind of oscillating. Why is it oscillating? Why is it sometimes higher, sometimes lower?
Because there's gaps in infection rates of infection based on how much people that get infected.
Yeah, so it depends a lot on the vagaries of where people are infected, etc. You still see some big swings, though. This is not totally just noise around this. There's actually some swings here as whole areas get infected, and then they're no longer subject to infection, and then the amount of infection that can occur is limited by that, and you'll notice there's big swings. But roughly around 37. Okay, suppose we now up this here to be a situation where we have a population of size 500. Maybe someone could get that other door there. I don't want to trouble those using the computers out there. Okay, population size 500. Great, ladies and gentlemen. So here we have population size of 500. Notice once again this exponential rise, right? That we tried to explain that later. Is the sort of the mean rate of infection that you see the same as before or different? So we approximately doubled the size. Is the prevalence of infection the same, the fractional prevalence? Well, you know, here we have a prevalent case count. We'd like to perform something with the fractional prevalence. So ladies and gentlemen, I'd like you to actually go, and we're going to, at the cost of changing things a little bit, what I'd like you to do is to go to the population here, okay? And I'd like to add in a statistic like this one, but with a fraction that are infective. So this would be called fractional prevalence. It's a fraction infective, okay? So can anyone help me understand, given the semantics of the choices here, what's one way to compute prevalence? Is it a count? We're counting the fraction that are infective. Is it a count? How do you think we could do it? What's one way?
Number of infected divided by the population size.
Okay. Yeah, so something about the population size. It turns out we can be a little bit clever about it. We could take an average here, and I would argue we could take an average over what expression? You could think of the fraction of people that are infective as being an average over what? Okay, yeah, so if someone's infective, we'll treat them as 1.0. Otherwise, they're 0. And I would argue an average over this infection over the entire population. Almost by definition, an average is like summing this up divided by the number of things being averaged, right? If you take an average of two numbers, what is that? It's the sum of the two numbers divided by 2, right? If you have an average over 10 things, it's the sum of the 10 things divided by 10. This is an average over this, so it's going to be summing up. For each person that's infected, it's going to be 1. Otherwise, it's going to be 0. And it's dividing by the number of people in the population. So it's an average like that. That's the fractional prevalence. Infective. Okay, great. So let's go up to our chart here. Let's go up to our handy chart. And let's go now have a value here for each of these. So for the aggregate model, we're going to use fractional prevalence of infectives, fractional prevalence of infectives, this guy right here, this whatever you called yours, I called it fractional prevalence of infectives. Maybe for you called it fraction infected or something like that. So that's one thing. That's the aggregate. And then for the ABM, instead of doing count infective, I want to do fractional prevalence infective. That's just the statistic we just defined. So what did I do? I went to population. I defined this new statistic called fractional prevalence infective, and then I went up to here and I had it depend on those instead of the absolute preference. Fractional prevalence infective, I call that, it's a method in population, so make sure you put in those begin paren, end paren, and this guy is just referring, ladies and gentlemen, to this variable here. Okay, so let's run this thing. Let's do it for, the reason I wanted to see fractional prevalence is I want to be able to compare the effects with different numbers of people there in the population. Okay, so here we go. It's rising, and there we go, and it sort of reaches about 0.15 average. Pretty good representation with the aggregate in terms of the mean. Great. Okay, now let's run it with population size 500. You think it'll be 0.15 or different? What's same, what's different about this population? Population is twice as high. Pretty similar. Pretty similar, ladies and gentlemen. Pretty similar. Okay. Let's go and make the population size, let's take that, let's make it half that population size, right? So instead of being 250, let's make it population of 125. 125 population size. There we go. 125. What do you think the effects will be now? Same or different? Fractional prevalence. What has changed? What has changed here, ladies and gentlemen? Population size did, almost by definition. But what else has changed? Pretty similar average for the aggregate model. The aggregate model hasn't changed at all in terms of its behavior. What's changed in the ABM model? Did we change contact rate? What did we change? Yeah, so the number of connections. Can you see where this is going? Okay, so those are pretty similar there. How far can we take this? Suppose we made it a population size of 50. Do you think it's going to yield the same results? 50. What do you think is going to happen? So within a certain range, it's okay. But what are we bumping up against as we're lowering this?
Your infection's going to die a lot.
Can you control it more by keeping the seed the same instead of random?
Yep, we could do that. In fact, this by default has a. Okay, so each new experiment has a new one. If you do random seed, yes, you could control that, but the problem is that the seed is going to be affecting the layout of the network as well. So that's going to throw it off as different. It's not going to be quite the same here. You're going to start to have a lot more die out. And fundamentally, ladies and gentlemen, this network is not going to be connected. And what that's going to mean is that you're not going to get the spread of persistent infection like you did before. And there's going to be a critical threshold where that starts to be a really big effect. And it's somewhere between 50 and 125 that it becomes a very big effect. Even at 125, I would wager that if you ran this, it will tend to die out more quickly. It will tend to die out more quickly. Why is that? Anyone? Why would this die out more quickly? Look at that. It's dying out very, very quickly compared to before with 125. Why? Okay, so that's true at a kind of high level. The number of connections are not high enough to sustain. But let's talk in terms of concrete. So let's talk in terms of very particular situations. Change this to a random seed to make it more meaningful. what in concrete terms, give me an example about how they could be different. With a sparse network like this, why could its effects be different than what we see in a denser network, a network where people have more connections?
Well,
There's not as many cluster areas that have large
Good.
The infection doesn't have time to like survive while people are recovering. It's like while people are recovering, the infection will die out with 125 people, but if there's 250,
Yeah.
while those people are recovering, it'll like survive another like population. Like
It's somewhere else in the network.
Yeah.
Okay, so yeah, let's think about a couple things that could occur. First is there could be a recovered person who's located along a key pathway of sort of movement to the infection. We start to have to think about what's called percolation effects where the infection needs to get from A to B. It has to get over to a new area. I think this is what Jordan was referring. Let's suppose the infection's in this area. It's not going to be able to get over here if there's even one person blocking it here. If this person is recovered, it's not going to be able to go over there. So there's constraints there. Another issue is, beyond that, there's issues having to do with, okay, maybe I have a contact rate that's the same for these different scenarios, but here I'm contacting the same people repeatedly. Again and again and again and again, I'm contacting the same people because I have a small number of neighbors. This person here on the outskirts of this network, they're contacting these two people again and again and again. And if both of them are infected, they're not going to infect any more people. So the contact rate, it would be a problem to say, well, the contact rate is, 10 people per day. I'm sick for 10 days, and so I've contact with a total of 100 people, so I could infect all of them if the population is susceptible? No. Because I have a contact rate of 10, but it's with certain small number of people, and I can only infect a certain number of them. So even here, we see actually some quite big differences. At some point, the network becomes fragmented, and then there's no way you're going to get a large prevalence. But even here, you get the infection to die out very quickly in many cases. So ladies and gentlemen, these are big differences over density. And you'll notice that this is one of the things. We are changing the density of the network as well as changing the population. And when I was talking earlier about doubling the area, I was referring to the fact that often we only want to change one thing at a time. We want to change population size, but keep density the same. So what could I do if I wanted to change the population size here from 250 to 500, but not have the density of people go up, the density per unit area number of people? What could I do? Change the area, right? I can make the area larger. And in fact, if you go here in AnyLogic, we laid the groundwork for that. Some of you may remember when we defined this population, we defined it so that people are laid out with a certain space width and space height. So here, I could have a population of 500. I'm going to copy this, and I'm going to do paste, and I'm going to say pop 500, same density. Okay? So baseline density. Probably I should say baseline density. It's a little bit ambiguous there. Baseline. In other words, same density as in the baseline model, baseline run. And here, ladies and gentlemen, I can go set, actually, it's going to be, excuse me, I stand corrected. It's going to be in main, down in main, and you notice there's a space width, space height. So really, I'd have to specify it with parameters. I should really have specified it with parameters. If I double the population, do I double each of space width and space height? No, I'm multiplying by what? 0.2, square root of 2 each. Or I could double one, retain the other, for example. That will lend a little bit of a difference. But I should have encoded that with parameters. So here we're going to have a wider space, but retain the density of the original. Okay. Anyway, ladies and gentlemen, here's a situation where we have network effects. We have effects as we shrink the density of people, the network becomes fragmented, and also there's differences in the number of people that can be infected. Okay, so I'm going to go back to main and change this back to be 500 by 500. It's one more reason to use parameters. You don't modify the model. Okay, now my attention wants to turn to a different thing. So, ladies and gentlemen, comparing the ABM with the aggregate model, what differences are we seeing here? What are the major differences here?
There's a lot more base model.
Good. Essentially, there's essentially none in the aggregate model. It's differential equations that are with, you have dx dt equals a very well-defined thing. So you have essentially none here. Are they totally dissimilar?
No.
So what parts of one are relevant to the other? So if we run this, what things do you see from the aggregate model, this guy down here, that have some relation to what's seen in the ABM?
The actual movement of how they move, like the multiplies.
Okay, so at the beginning, they're very, very similar here. This initial infection spread, they're very, very similar, right? They're almost on top of each other here. So I'll call up a navigation here. View. And we'll zoom in there. They're almost atop each other here. Where else is there a distinct similarity?
The average of the ABM model is probably pretty close to the equilibrium.
Yeah, the average of it. The average of it is pretty close, it would appear. I mean, we could go stick in a statistics object, right? You've used those before, but, go here, we stick in a statistic, and this will be, prevalence statistics, statistic, and maybe we'll update every 1 day, something about the prevalence. And here we'll do it, we will update population dot, and it was fractional. Here we go, fractional prevalence infective. So let's try running it. And I would argue that you will probably see, here we go. Oh, it died out. Okay, there's some limits to this, but let's, for the initial period, do it. Okay, here we are, it's spreading. Here we are, it's kind of getting it to a dynamic stochastic equilibrium. It's going around this equilibrium point, but with oscillations, and I'm going to check out this prevalence statistic. Okay, so the mean is 0.128 for the baseline. Meanwhile, the fractional prevalence of infectives is 0.143. Close. Let's suppose if I go to a population of 500. Let's go check it out there. Okay. Do you think it'll be closer or further between those two then?
Closer.
Force of infection is again 0.143. Here we have a mean of 0.137. Quite a bit closer. Suppose we were to go to a population size of 1,000. What do you think we would see there? Closer yet? Why? What's going on? Why is it getting closer? Sample size is increasing. Yeah, okay, fair enough. Sample size is increasing. So there's less random variability in in terms of these estimates. But what else is going on?
You're losing the geographic randomness.
Yes, we're losing a lot of geographic randomness. Ladies and gentlemen, as this is going on, we're getting closer and closer to something where you'll notice here it's 0.14, to where it's getting closer to well mixed. And here, of course, we had a population size of 10,000. Here we go. Okay, this is going to be fun. Okay, here's 10,000 people. Okay, it's initializing it. I think I pressed that button. Yep. Look at this. It's allocating memory. This indicates it's in a memory-constrained regime. Okay, it's red. So I'm going to close this for a minute. I'm going to actually go allocate it more memory. So ladies and gentlemen, with this population size, particularly those pursuing projects may want to be aware of it. You go to this, you could set maximum available memory. I'm going to give it a gig here. Okay, here we go, 10,000. It actually uses a lot of memory just for visualization, and that can be avoided for certain types of runs, but here we actually would like to see the visualization. Okay, so here it's allocating memory. It's setting up each of those agents. It's laying them out in a network. It's determining connectivity, etc. And in the fullness of time, it will start to run. Come on. Surprised it's taking this long. Okay. Here we Dropping. Oh man, my machine is memory constrained. Not any logic. Okay. Let's see what else I have running here. Oh no, you don't want to look at Scala. That'll be for 816. Yeah, okay. Yeah, I'm recording video and terminal and under Ubuntu sometimes takes a god awful amount of memory. I think it's a memory leak. Okay. Back to this. Is it running on your machines? Running or not? Does that mean not? Is it running? Still not. Okay, well, take it from me. It'll be getting closer to a situation as depicted by the aggregate model. And we're going to investigate this. Okay, ladies and gentlemen, what else? Now, what is different between these two? So, I may fool around with this a bit. Maybe I'll do this for a population of 4,000. What else is different between these two? What is different between the two? One is stochastics. Alex mentioned that earlier. What else?
The timeouts in the agent-based model, it's not like the mean time
Good.
duration like the SD model.
Exactly. Yeah. So we're dealing with a situation where instead of being just an average time of a memoryless process, it's actually based on a timeout. Okay. So that's different. Extinction is different, ladies and gentlemen. It does go extinct, and that's a matter of stochastics. It's a matter of the fact that it is something which can by chance go extinct. There's this phenomenon of saturation. You can only infect so many people around you before you recover, and that's dictated by the number of people to whom you're connected. Okay, so a lot of features here, some similarities, some differences here. Okay, we're now going to continue on to look at this issue of networks and the types of networks that we have in place to examine how do those end up affecting the dynamics of a model. So I'd like to talk about AnyLogic's several types of networks, okay? And We're going to do so in an interactive way. So we're going to actually be exploring these things interactively as we see the different types of networks. And there's going to be a handful, about 5 of them, that we're going to talk about as sort of network exemplars. Okay, so ladies and gentlemen, where are networks encoded in this model? Where was our assumption about what network type we wanted to use incorporated in this model?
In Maine, I think.
Okay, it was indeed in Maine. That's correct, yeah. So, okay, my machine is still exhibiting slowness here. I think it had a hard time killing that simulation, and I'm surprised at the fact that it's still kind of slow. Give me a second, and this will, I'm just going to go call up the network slides here. What I'll also do is stop the recording for a minute so we can